All right. Good morning, everyone. Are there any questions? Okay, so let's take a look at that. Hold on. All right, so if we take a look at that particular problem, all right, so for the curvature, so kappa is going to be 1 on the magnitude, the velocity times the magnitude of the derivative of the unit tangent. Okay, so for the velocity vector, okay, so for that particular problem, for the uh, velocity vector, you should have that v of t is equal to 1 in the ith direction plus one over a squared sine hyperbolic of t over a. Okay, so if we look at the magnitude of this, we're going to have the square root of 1 plus 1 over a to the 4th times the sine hyperbolic sine squared of t over a. Okay. All right. So by our identities, real quick. So for this, it's what we can. Let me look at that closely.
I'm not sure. I only got the sine hyperbolic t over a in the j direction, like for the velocity vector.
Well, you've got to make sure that when you take the derivative of that, derivative of the first component should be 1 in the I direction. Derivative of the second component, you do have to make sure you use the, you got to use your chain rule. So, because if you take the derivative of the angle, you're going to get 1 over A. So, that's where I'm messing up. Okay, hold on. I looked at it wrong. That's gone. So this doesn't exist. Okay, so we should end up with, this is going to be the square root of the cosine hyperbolic squared of t over a, or just cosine hyperbolic of t over a. Okay, I misread the problem. Okay, so that's what you got here. All right, so when you do the unit tangent, so you've got 1 over the magnitude of the velocity times the velocity. So it's going to be 1 over cosine hyperbolic of t over a times 1 in the I direction plus sine hyperbolic of t over a in the j direction. So you should get secant hyperbolic of t over a plus tangent in the I direction, excuse me, plus tangent hyperbolic of t over a in the j direction. So you get that for your unit tangent?
Yeah, I got it correct.
Okay, so if we take the derivative of this, it's going to be negative secant hyperbolic of tangent over t over a tangent hyperbolic of t over a. But don't forget to multiply it by 1 over a. And this is going to be in the I direction. Plus, and then the derivative, second piece is going to be secant hyperbolic secant squared of t over a. And don't forget to multiply that by 1 over a in the j direction.
Oh yeah, I think I messed up that part. Like I forgot to multiply my 1 over a.
Okay. So when you do look at the magnitude of this, right? So the magnitude of dt dh, dt dt, that's going to be the square root of secant hyperbolic squared of t over a, and then you're going to have tangent hyperbolic squared of t over a, and then you're going to have that multiplied by 1 over a squared, plus, then for the second piece, I'm going to pull the 1 over a squared out front for the second piece. So it's going to be 1 over a squared times secant hyperbolic secant to the fourth of t over a. Okay. So for this, you can factor out a 1 over a squared and take the square root of it. So that gives you 1 over a. And then as far as on the radical is concerned, you can factor out a secant hyperbolic secant squared of t over a from both terms. So that leaves you with tangent hyperbolic squared of t over a plus secant hyperbolic squared of t over a. Okay, and then by your identities, we can get that tangent. That's going to, the second piece here is 1. So we get 1 over a times the square root of hyperbolic secant squared of t over a times 1, or we just end up with 1 over a times hyperbolic secant of t over a. So that's what you should have for the magnitude of dt dt. Any questions? So if I plug that in, okay, so we're going to have 1 over cosine hyperbolic of t over a, and then we're going to multiply that by 1 over a secant hyperbolic of t over a, and that should give us a 1 over a hyperbolic secant squared of t over a, which is what I think I have. Yeah. Okay. Any other questions? Okay, so let's pick up where we left off at for dealing with the section over tangential and normal components of acceleration. All right, so we were kind of on our last 2 examples. We were working on an example of we had that R of t is equal to e to the t sine of 2t in the I direction plus e to the t cosine of 2t in the j direction plus 2 e to the t in the k direction, and we're told that t is equal to 0. Okay, did we get through all the pieces of this? Okay, so we found, did we find the torsion? Okay, so we were ready to find the torsion in the next. Okay, all right. All right, so for the torsion, I gave you a variation for that formula, and what we're going to do is to use that variation. Okay, so the variation for torsion is that tau is equal to, we're going to do the cross product of the first and second derivative, and then dot it with the third derivative, divided by the magnitude of the first, the magnitude of the cross product of the first and second derivative, dot it and square that. Okay. All right, so the first derivative, which is velocity, what do we say the final answer for that was? That was in the ith component plus
Negative 2 e to the power t sine 2t plus e to the power t cos 2t in the j direction.
Okay. And then plus 2e to the t in the k direction.
Yes.
Okay. All right. So this is what we ended up with this. So what we're going to do next is we need to, I would have to make up the worst problem. Okay, I'm going to hold out on torsion on this because it's really, this problem is really ugly. I'll do the torsion for the next problem and show you how it works. So we're just going to ignore this on this one just because the derivatives on this are going to get really, really ugly. And we've got to do 2 more. Okay, is everyone okay with that? All right, so let's look at the next problem. Okay, so we have this next example. We have that r of t is equal to t in the I direction plus 1/2 e to the 2t in the j direction. And we're told that t is equal to the natural log of 2. Okay, so what I'm going to do is I'm going to go ahead and do all the derivatives for this because we're going to need it for torsion. So r prime of t is just going to be I plus e to the 2t in the j direction. R double prime of t is just going to be 2e to the 2t in the j direction. R triple prime of t is going to be 4e to the 2t in the j direction. Okay. Any questions there? Okay. So now what I'm going to do is let's go ahead and find the unit tangent. Okay. So really the only piece that we're missing is the magnitude. So for the magnitude of this, all right, so for the magnitude of this, we're going to have the square root of 1 plus e to the 4t, and there's nothing we can do. That's the best we're going to get out of that. Okay. We do not need the 4th derivative. Okay. We only need up to the 3rd as far as torsion is concerned. Okay. All right. So next, so we've got this. So for our unit tangent, it's going to be 1 over the square root of 1 plus e to the 4t. And then we're going to multiply it by the velocity vector, which is 1 in the I direction plus e to the 2t in the j direction. Okay. Any questions there? Okay, so now what I want to do is to find what the unit tangent is when t is equal to the natural log of 2. Right, so I want to find what the unit tangent is when t is equal to the natural log of 2. So if I plug natural log of 2 in this piece here, what will I have? So if I evaluate the magnitude of velocity at the natural log of 2, what will it give me?
One over root 5.
It's not going to give us that. Okay, so let's look. So we're going to have this. If we evaluate this at the natural log of 2, so it's going to be the square root of 1 plus e to the 4 natural log of 2. So it's going to be the square root of 1 plus e raised to the natural log. So it'll be 2 to the 4th, which is going to give me 16. So it's going to be the square root of 1 plus natural e to the natural log of 16 is just going to give us what?
16.
So we're going to end up with what?
17. Root 17.
So we're going to have 1 over the square root of 17 times I plus, now if we put the natural log of 2 here, and for this piece, we're going to end up with just a value of what?
4.
Okay, in the I direction. Okay, so there's our unit tangent. Okay. Any questions? Okay, so next, let's move to finding the unit normal. Okay, so the unit normal is going to be 1 over the magnitude of the derivative of the unit tangent times the derivative of the unit tangent. Okay, so if we do this, all right, so we need the derivative of the unit tangent. Okay, so here's the unit tangent. All right, and we need the derivative of this. It's going to be a little ugly, but it's going to come out nicely in the end when we evaluate it. Okay, so, and I'll write the tangent here. So it's going to be 1 over the square root of 1 plus e to the 4t and I plus e to the 2t over the square root of 1 plus e to the 4t in the j. Okay. All right, so if we take the derivative of the first component, we're going to end up with this. We're going to end up with negative 1/2 times 1 plus e to the 4t to the negative 3/2 times 4e to the 4t. Okay, and this is in the I direction, plus, and for the second piece, there's no easy way. You can change it to switch it up to a product rule, or you can use the quotient rule. It doesn't really matter. I'm going to do it as a quotient rule. So it's going to be the bottom times the derivative of top minus the top. I'm running out of room, so let me wrap this around. So, okay, so bottom times derivative of the top minus the top times derivative of the bottom, which is going to be negative 1/2 times 1 plus e to the 4t. Oh, excuse me, positive 1/2. 1 plus e to the 4t raised to the negative 1/2 power times 4e to the 4t over the bottom squared, which is going to be 1 plus e to the 4t. So this ugly thing, and this is in the j direction. Okay. All right, so the first piece is going to simplify down to negative 2e to the 4t over 1 plus e to the 4t to the 3/2 power. Write it back as a fraction in the I direction, and plus. Now for the second piece, if we take a look at this, we just need to, we're going to have to clean this up. Let me see. Let me go over 2 slides and clean this up. Well, you can go back a couple of slides and clean this up. All right, so if I take a look at this and clean this up, the second piece, so we have 2e to the 2t times the square root of 1 plus e to the 4t. Okay, and then we've got minus for the next piece. I'm going to go ahead and multiply this and this together, so that's going to give me 2, and then multiply these together, and that's going to give me e to the 6t. 2e to the 6t, and we're going to multiply that by 1 plus e to the 4t to the negative 1/2, and then this is over 1 plus e to the 4t. Okay, so what I'm going to do is a little factoring here to reduce, and it's the numerator that I'm going to be factoring. Okay, so from the numerator, I notice that I can factor out a I'm going to factor out a 2e to the 2t, and I'm also going to factor out a 1 plus e to the 4t to the negative 1/2. So I basically factor out everything with the smallest exponent. Okay, so what I have left in the numerator, when I take 2e to the 2t from 2e to the 2t, I'm left with 1. If I factor out 1 plus e to the 4t to the negative 1/2 from the square root of 1 plus 4e to the 4t, I'm going to be left with 1 plus e to the 4t to the first. Okay, so one of the things you have to remember is that when you are factoring, essentially, as far as rules of exponents are concerned, you are subtracting the exponents. Okay, so you have to understand that the square root is the 1/2 power. So I've got 1/2 power minus a negative 1/2 power, which gives me a power of 1. Okay, then minus, we took out the 2, we got e to the 2t we're factoring out, we've got e to the 6t, so that leaves me with e to the 4t remaining, and then this whole last term is gone. Okay, and then this is over 1 plus e to the 4t. Right, so what happens now when we look at this, e to the 4t's cancel, which is nice. So really what I'm left with in the numerator is 2e to the 2t. This term I'm going to take to the denominator. So it's going to become 1 plus e to the 4t, and it's going to be raised to the 3/2 power. So this is what this cleans up to be. Any questions? Okay, so let's put that in. So in the second piece here, we had that it was going to be 2e to the 2t over 1 plus e to the 4t to the 3/2 power in the j direction. Okay, so that is what dt simplifies down. Simplifies down to. Any questions there? Okay, so what I'm going to do at this time is I am going to cheat a little bit, and I'm going to go ahead and evaluate dt at the natural log of 2, and then do the magnitude to make my life easier. Okay, so if I take the derivative in respect of the unit tangent in respect to time, I'm going to evaluate it at t equals natural log of 2. Okay, so when I do that, when I put the natural log of 2 into this first piece, I'm going to end up with -2 times 16. So I'm going to end up with -2 times 16 is not -34. It's going to give me -32 over. Then for the denominator, when I put in the natural log of 2, I'm going to have basically this expression here is going to end up being 17 to the 3/2 power. So, and I'm going to leave it as 17 to the 3/2 power. And that's in the I direction. Then plus. Then for this top term, if I put in the natural log of 2, I'm going to have 2 times 4, which is going to give me 8. And the denominator is going to be the same, so it's going to be 17 to the 3/2 power in the j direction. Any questions? So the magnitude of this, it's going to make the magnitude a lot easier to deal with. So we're going to have 32 squared, which is going to give us what? So it's going to give us 1,024 over, if I square the denominator, it's going to become 17 cubed. Plus, next one's going to be 64. The denominator is going to be 17 cubed. Okay. So we're going to end up with the square root of 1,088. 17 cubed is going to give us 4913. Okay, and I don't think that will clean up any. It does simplify down, which is nice. So it does end up simplifying down to the square root of 64 over 289. So if you take the square root of that, you're going to get 8 on top, and for the bottom, it should be 17. Okay. So it cleans up nicely to 8 over 17. Right? Any questions there? Okay, so let's do the unit normal, and we're going to do the unit normal in the evaluated form. Okay, so if we take a look at that, we're going to have 1 over. All right, so the magnitude of dt dt was 8/17, and then we're going to multiply it by, okay, and we found that dt was negative 32 over 17 to the 3 halves in the I direction, plus 8 over 17 to the 8 over 17 to the 3 halves in the J direction. So essentially, as far as this is concerned here, what is this actually equal to? So what's 1 over 8/17 equal to?
17 over 8.
Right. Okay. So let me go ahead and write that way. This is going to give us 17 over 8. And then if we multiply this out, we're going to end up with negative 4 over 17 to the 1 half in the I direction, plus 1 over 17 to the 1 half in the J direction. Now, if you write it as a square root of 17, that's the same thing as 17 to the 1 half. Any questions? Okay, so for this, the next piece, which is going to be the binormal, okay, so I keep deleting those out. For the binomial, again, we're going to look at it when t is equal to natural log of 2. All right, so it's going to be the cross product, so we're going to have our I, J, and K. Okay, so we're going to take the unit tangent. We found that the unit tangent, oops, didn't go back far enough. We find the unit tangent to be 1 over the square root of 17 in the I plus 4 over the square root of 17 in the J. So 1 over the square root of 17 in the I, 4 over the square root of 17 in the J, and we're going to put 0 for K. And then for the normal, we found it to be negative 4 over the square root of 17 plus 1 over square root of 17. So negative 4 over the square root of 17, 1 over the square root of 17, and then 0. Okay. So if we start looking at this, all right, so for the I component, we're going to get 0. For the J component, we're going to get 0. And then for the K component, we're going to get 1/17 plus 16/17, or just 1 in the K direction. So my binomial vector is just K. Any questions there? Okay, so next we need to find curvature. So we know that, and again, it's kappa when it's equal to the natural log of 2. All right, so we're going to take 1 over the magnitude of the velocity times the magnitude of the derivative of the unit tangent. Okay, All right, so what did we say the magnitude of the velocity was at the natural log of 2?
Root 17.
Okay. And then what did we say that was the magnitude of the derivative of the unit tangent at natural log of 2?
8 over 17.
Okay. So what we're going to end up with is going to be 8 over 17 squared root of 17, or you can write this as 8 over 17 to the 3/2. And that will represent our curvature. Okay. Any questions? Okay, so the last thing we're going to take a look at is going to be the torsion. Okay, so for the torsion, again, our formula is going to be r prime crossed with r double prime dotted with r triple prime divided by the magnitude of r prime cross r double prime squared. Okay, so what we're going to do first is to find r prime cross r double prime. Okay, so again, we're in the IJK, right? So we did that at the beginning of this, took those derivatives because I knew we needed them later. Okay, so we're going to have for this 1 plus e to the 2t. Then we're going to have just 2e and 2e to the 2t and 4e to the 2t. So when we look at this, so we're going to have 1 e to the 2t 0. Then we're going to have 0, 2 e to the 2t 0. And then and that's it. Okay. All right. So if we evaluate this, okay, so for the I component, we're going to get 0. For the j component, we're going to get 0. And for the k component, we're going to get 2e to the 2t minus 0, or 2e to the 2t in the k direction. So now, since we're here, we're going to go ahead and find the magnitude of this. So if we do the magnitude of r prime cross r double prime, okay, so it's going to be the square root of 4e to the 4t, which is just going to give us 2e to the 2t. Okay, so if we plug in, so in place of this, I'm going to put in 2e to the 2t in the k direction. We're going to dot it with r triple prime, which we said was 4e to the 2t in the j direction, over the magnitude, which is 2e to the 2t, but we do need to square that. Now, as far as the dot product is concerned of the numerator, what is it equal to? Yeah, so it's equal to 0 over 4e to the 4t. So our torsion is 0. Okay. Any questions there? Okay. All right. So that concludes everything from that section. Any questions? Okay. All right, so let's look at our next section. All right. In our next section, we are going to be dealing with velocity and acceleration in polar coordinates. Okay. All right. So, kind of the reason why we're taking a look at this. The material here does kind of deal with in terms of dealing with physics and also astronomy. Okay. A lot of this generates around Kepler's law. Okay. But what we're going to look at it is in terms of just um, doing a problem in that being able to rewrite the velocity vectors in terms of um, two other vectors that may be in terms of r and theta. Okay. Now, the kind of our approach here is going to be similar to what we were doing when we were trying to write the acceleration vector in terms of um, a unit tangent and a unit normal. Okay, so it's kind of going to be the same approach. All right, so we're going to write the velocity vector in terms of u of r and u of theta. Okay, and these are just two different vectors, one vector made up of in terms of r's, another vector made up in terms of theta. We don't necessarily know what those vectors are, and we're not concerned to find those. Okay, so for the velocity vector, it's going to be equal to r dot u of r plus r theta dot u of theta. Okay, now what the dot means above the r and theta means that you're going to take the derivative of it. Okay, you're going to take the derivative of it. So one dot means the first derivative. If it was two dots, it would be the second derivative. All right. Now, the acceleration vector written in terms of u of r and u of theta. So acceleration is going to be equal to, all right, so we're going to have r double dot minus r theta dot squared in the direction of u of r plus, we're going to have r theta double dot plus 2 r dot theta dot, and this is in the u sub theta direction. Okay. And these are the formulas that we're going to be using in order to do this. Okay. Any questions? Okay, so let's take a look at a first example. All right, so our first example, we are told this, that r is defined as a sine of 2 theta, and we're told that d theta dt is equal to 2t. So if we deal with the velocity vector, all right, so again, the formula is going to be r dot times use of r plus r times theta dot times use of theta. Okay, all right, so r dot means that we are going to take the derivative of r, okay, and we're going to take it, we're going to take the derivative in terms of theta. All right, so if we take the derivative of this in terms of theta, we're going to end up with 2a cosine of 2 theta. Okay. Now, for this piece here where we've got theta, d theta dt, that's the same thing as theta dot, okay, because that is the first derivative. Yes, a is a constant. Okay. All right. So if we fill this in place of r dot, we're going to put in 2a times the cosine of 2 theta, and this is in the u of r direction, plus we're going to take r, which is defined as a times the sine of 2 theta, times theta dot, which is 2t, and this is in the u of theta direction. Okay. So basically what we're going to do is to clean this up. All right. So if we clean this up and I goofed up just slightly here. When we're doing r dot, it's the derivative in respect to time, okay, because it does have to match the variable here. So we got to multiply this by d theta dt. Okay, so for this, for this first piece, I've got to add in just a little bit more. So I've got to multiply this by d theta dt, which is 2t times u of r. Okay, so when we're taking the derivative, we're always going to take, if everything, unless everything is defined in terms of one variable, you're always going to take the derivative in terms of, we're going to take derivative in terms of time unless otherwise told. Okay. So if I clean this up, so for the first piece here, if I clean this up, that's going to give me 4 t times a times the cosine of 2 theta in the u of r direction, plus then for the second piece, if I clean this up, and my cleaning up is just to pull things up front, okay? So we're going to have 2ta times the sine of 2 theta in the u of theta direction, okay? So that will be our velocity vector. Any questions? Okay, so excuse me, for the acceleration vector, all right, so it's going to be defined as r double dot minus r times theta dot squared in the use of r direction, plus r theta double dot plus 2r dot theta dot in the use of theta direction. All right, so if I take a look at this, I've got r dot and theta dot. I don't have r double dot, and I don't have theta double dot, okay? So let's find those real quick, okay? So what would theta double dot be for this? So we're taking the,
Just 2.
it's just going to be 2, okay? Then next, we need to find r double dot. But in order to help us find r double dot, I'm going to replace d theta with 2t. Okay, I'm going to replace d theta with 2t. All right, so simplifying this a little bit, so that means that r dot is really going to be 4ta cosine of 2 theta. Okay, so now I'm ready to find r double dot. Now, when I do that, okay, my variables are actually theta and t. Okay, so I'm using 2 different variables here, so I'm going to have to use a product rule. Okay, so I'm going to say this is my first, this is my second. So if I take the first times derivative of the second is going to be negative 2 sine of 2 theta times d theta dt, okay, chain rule, plus the second times the derivative of first. And when I take the derivative first, keep in mind that I am taking the derivative with respect to time. So if I take the derivative first, I'm just going to end up with 4a. Okay. Any questions there? All right, so now what I'm going to do is to fill into the formula. So r double dot, what we're going to do, we're going to put it in as, now keep in mind, in place of d theta dt, we're going to put what in its place? 2t. So 2t goes here, all right? So I'm going to have 2t times negative 2 times 4ta, which is going to give me what? So again, 2t times negative 2 times 4ta is going to give me what? You're close, but not quite. So negative 2, and 4 gives me what? If I multiply those together. Yes, we should have negative 16. So we're going to end up with negative 16 t squared a. Okay. Then we're going to have that multiplied by the sine of 2 theta. Then we're going to have plus. Then for the other piece, we're going to have 4a cosine of 2 theta. Okay. So that's what r double prime is going to be equal. Double dot is going to be equal to. Then we're going to have minus r, which is defined as a sine of 2 theta, times theta dot, which is 2t, but we're going to square that, so that gives us 4t squared there. And then this all is in the u of r direction. Any questions there? Okay. Now, I've kind of run out of space, so I've got to write the rest of this on the next page. Okay. So let me switch over. So let me start it off again. So we're going to have that acceleration vector starting off is going to be negative 16t squared times a times the sine of 2 theta plus for a times the cosine of 2 theta. Then we got minus, and we're going to have a sine of 2 theta times 4 t squared in the use of r. And we're going to plus, okay? Now, for the second piece, we're going to start off with doing r times theta dot. So r, which is defined as a times the sine of 2 theta, theta double dot has a value of 2. Okay, plus 2 times, all right, r dot we found to be 4t a times the cosine of theta times theta dot, which we said was 2t. And this is in the u of theta direction. All right, so now we just have the fun time of cleaning everything up. Okay, so if we look closely, we'll realize that this and this are going to be like terms. Okay, so if we combine those two pieces, what do we end up with?
Negative 20.
So negative 20 t squared a sine of 2 theta plus the other piece just comes along, and this is in the u of r direction, plus. All right, if we look at the second piece, are we going to be able to combine anything?
No, but we can skip by.
We can't combine, but we can just put we can put things together to make it look a little bit cleaner. So we can have, in the second piece, we're going to have 2a sine of 2 theta plus, we're going to end up with 16 t squared a cosine of, and this is my fault, that should be a 2 there in front of that, 2 theta. In the u of theta direction. Okay, so that would be our vector in terms of our acceleration vector in terms of u of r and u of theta. Any questions? Okay, so let's do one more example. All right. In our last example is that r is defined as a times 1 plus the sine of t All right, so r is defined as a times 1 plus sine of t, and theta is defined as 1 minus e to the negative t. Okay. All right, so for all our pieces, we need up through the second derivative. And keep in mind that we're taking the derivative in respect to time. Okay, so in the case of this, it's a little different in that both pieces are defined in terms of time. So we don't have to do anything extra like we did in the first example. Okay, so r dot, what would that be equal to? So what would r dot be? It won't be a sine t, excuse me.
A cosine t.
Yeah, so it's going to be a times the cosine of t. What's r double dot going to be equal to?
Negative a sine t.
Okay. All right. So next, let's find theta dot. So what's that going to be equal to?
E to the power t.
Be e to the negative t.
Negative t. Yeah, my bad.
And then theta double dot, what is that going to be equal to?
Negative e to the power negative t.
Okay. So we basically have all our pieces. So all we're going to do is just now fill into the formula. Okay. All right. So we know that the velocity vector is defined as r dot in the use of r direction plus r times theta dot in the use of theta direction. All right, so in place of r dot, we're going to put a cosine of t plus in the use of theta direction, we're going to do r times theta dot. So we're going to have, I'm going to write it as a times e to the negative t times 1 plus sine of t in the use of theta direction. And that's about as clean as you're going to get this. You're not going to get it much cleaner than this. Any questions? All right, and then for the acceleration vector, okay, so we're going to do r double dot minus r theta dot squared in the use of r direction plus r theta double dot plus 2r dot theta dot in the use of theta direction. All right, so r double dot, we said it was negative a sine of t. Theta dot, which is negative e to the negative t, but if we square that, it's going to become e to the negative 2t. All right, and we're multiplying that by r, so I'm going to put the a in front of the e. And then we're going to multiply that by 1 plus sine of t, and that's in the u of r direction. Plus, we got r times theta double dot. So if we do that, that's going to give us a negative a e to the negative t times 1 plus sine of t. Kind of running off a page here. Okay. Plus 2 times r dot and then multiplied by theta dot. So we're going to end up with a e to the negative t times the cosine of t. Okay, and this is going to be in the use of theta direction. Now, looking at this, there's nothing we can combine. So this is the best we can write the answer. All right. Any questions? Okay. Any questions over this section? Okay, so that's going to be it for today. I'm not going to start into the next thing of material because we're going to be moving into dealing with functions at that time. So I'm going to wait until Thursday to start that. Okay. All right. So at this time, you should be, as far as homework is concerned, homework over tangential and acceleration. Oh, excuse me, not acceleration. This is normal. Components of acceleration. And also velocity and acceleration in polar coordinates. Okay, so these two homeworks are in Canvas. You should be working on those. Okay, quiz 4, screwed up the time again. Sorry about that. You've got to 2 p.m. to get it in, and it's still due today. Okay. Quiz 5 is coming available, and it's due at 11 a.m. on Thursday. Okay, so quiz 4, don't forget about it. It is due today at 2 p.m. Quiz 5 is going to become available, and it's due at 11 a.m. Okay. Any questions?